Okay. Hello to everybody. So I am very happy to begin this workshop and to speak about the dynamics of Jouanolou foliation. So this this is a joint ongoing project with Aurélien Alvarez from the École Normale Supérieure in Lyon. And so I am going to report on some history of the dynamics of holomorphic foliation on the complex projective plane and on the affine plane also, before stating and speaking about our results. So there is a very famous result by Uday in the early 60s, which says that if you take a polynomial differential equation on the affine plane, complex plane, so here the function p and q are polynomials of degree d, that satisfy some genericity conditions that I'm not going to speak about. So then the solutions of this differential equation, either they are equilibrium points, so there are points where p and q are vanishing, or the solution is a Riemann surface immersed in C2, which is dense in C2. So it was kind of surprising to have such a phenomenon of density of orbits if you compare the situation in the real case, where we have the Poincaré-Benedictson theory, which states that orbits are accumulating on cycles. And so here the situation is much more complicated. So this theorem of Uday was improved and completed by Ilyashenko some years later. And before stating Ilyashenko's result, I will introduce some notion coming from dynamical systems, which is the notion of structural stability. So if you have a vector fields on a manifold, so here think of the vector field we had on C2, it is called structurally stable if, when you look at the phase portraits, namely the partition of the manifold into the integral curves of the vector fields, then this phase portrait does not change up to homeomorphism when we change a little bit the vector fields. So I made a picture with my hands. And so it is interesting to remark that this notion, in fact, does depend only on this partition of the manifold in trajectories of the vector fields. And so it depends only on the underlying foliation. So maybe this is, this historically, actually, this notion of foliation appeared approximately at the same moment, a little bit earlier, but not much earlier. So, as I said, Ilyashenko some years later improved the result of Uday, and he showed that under the same assumptions, so if you take again the same kind of differential equation, polynomial differential equation in C2, so he proved that in fact they are ergodic, namely you cannot find a decomposition of the phase space into a union of trajectories such that each of the atom of the partition has positive Lebesgue measure. So first, it is ergodic, and secondly, it is locally rigid. So this concept of local rigidity is the opposite of, it's an opposite, say, of the concept of structural stability. It says that if you perturb a little bit such an equation into another one, and you assume that the phase portrait of the two are the same up to homeomorphism, which is close to the identity, then in fact, you can take as your homeomorphism an affine automorphism of C2. So this is a strong opposite of the structural stability. So I wanted just to speak about the techniques that are used to prove these results of Udaj-Verenov and Ilyashenko. So the techniques is to compactify the foliation of the affine plane to a foliation of the complex projective plane, which is possible because we have algebraic differential equations. So the foliation can be compactified into an algebraic foliation of the complex projective plane. And it turns out that if you take a generic degree D polynomial vector fields of C2, then in fact the line at infinity, so this is a line that you add to C2 to get the projective plane. So it turns out that this line is a leaf of the foliation. When you take out a certain, you have also a certain number d plus 1 singularities at infinity, where d is the degree of the foliation of the polynomial equation in C2. So you get a leaf at infinity, which is a sphere minus d plus 1 point. And the main ingredient that they use is to look at the holonomy representation of this leaf at infinity, which gives you a representation of the fundamental group of this sphere minus d plus 1 point into the group of germs of diffeomorphism of the complex line fixing 0. And in fact, their results are consequences of related analogous results for subgroups of these groups of germs of diffeomorphism of the origin, fixing the origin. In fact, we now have a very good understanding of these groups acting at the origin, at the neighborhood of the origin, by results of Isao Nakai and Arseny Sherbakov. But as you see, you get some foliations that fix a line at infinity. And in fact, this is not at all a generic situation. Around the same time, in the 70s, Jouanolou proved that a generic foliation of the projective plane of degree D do not have any algebraic curve, algebraic leaf. And quite recently, so 15 years ago or 20 years ago, around 20 years ago, Franck Leray and Jules Rebello improved the results of Udaj-Verenov and Ilyashenko in the following sense. So they, instead of looking at generic differential equation of the complex plane, they looked at generic foliations of a given degree on a given projective space. So here the result is true in any dimension. So they proved that in this context, they were able to find a non-empty open set of the moduli space of degree D foliations of the n-dimensional projective space, which satisfies that all the leaves are dense, namely the foliations are minimal. They are ergodic in the same sense as what I was saying before, and locally rigid, also in the same sense as as in the Ilyashenko theorem. So here the difficulty is that you don't anymore have any group of germs of diffeomorphism available to study the dynamics. So instead of those groups, you have pseudo groups, and so they invented many techniques to study this pseudo group and to prove these three properties. So you have an open set, so to make a conclusion about all these things. You have an open set in the moduli space of foliations of a given degree and on a projective space of a given dimension of foliations that present a very, very chaotic behavior.
Bertrand, when you think about in the space of module, this means just a trivial equivalence.
Yes, the equivalence is that two foliations are equivalent if they differ by an automorphism of the complex projective space.
But what do you mean then by the moduli space of foliations?
So I mean the variety of foliations of a complex projective space mod by the group of projective equivalents in the sense of, so you can take it as a sense of GIT. I don't think it has really been studied in details, but you can just take it as a definition, or if you, or you can also state the theorems on the moduli space.
I just wanted to understand. In my school, two foliations which are affine equivalent belong to the same modulus class.
Sure. So
this means that any two closed points are distinct in the moduli space.
Exactly. Okay. Right. So here, locally rigid is just that if you take, you have a neighborhood. So if you take this moduli space, if you quotient by projective equivalence, local rigidity means that you have a neighborhood of your foliation such that any foliation in that neighborhood is not homeomorphic to your original foliation.
Exactly. Right. And now then about openness in this theorem, is it Zariski open? Or not?
No, not at all. Not at all. You will see. I will answer this question. So it is an open set for the so the usual topology. So, but not for the Zariski topology. So you will see that its complementary is open in the usual topology also. I mean, it has its complementary has non-empty interior. Sorry.
I see.
For some D and N. Okay, so I think I am finished with this history. So we have a lot of so I described many results showing that in the moduli space of degree D foliation of the complex projective spaces, we have very chaotic behavior, and in fact, I would like to describe a result that we obtained with, so as I said this earlier, saying that in fact we also have a completely distinct kind of behavior arising in these moduli spaces. So in fact we were able to prove that for degree 2 foliations of the complex projective plane. So the theorem is the following. So if you take the Jouanolou foliation, so of the complex projective plane of degree 2, so this is the foliation which is given by the following homogeneous vector fields in C3, which is given by this simple formula. So this foliation was introduced by Jouanolou because it was an archetypic example of a foliation of the complex projective plane which do not have any algebraic leaf, any algebraic solution. So all solutions are transcendental. And what we proved with Aurélien is that this foliation is structurally stable. So namely, any foliation given by, say, a polynomial equation in C3 close to that one will be topologically conjugated to the Jouanolou foliation. So this is one part of our results, and in fact, we also have some results about the dynamics of the Jouanolou foliation itself. So this is something which is well known, for instance, in the theory of Kleinian groups or the iterative theory of rational functions, which is in general, when you have structural stability, you also have a non-trivial decomposition of the dynamical system into a Julia set and a Fatou set. So this is what we prove. So we prove that this Jouanolou foliation has a non-trivial Fatou component. So I will not describe the theory here. So there were some different works to try to define what is a Fatou component for a foliation. So here, we analyze this Fatou component and we prove that in fact it is an open subset of the complex projective space plane, which is a union of leaves of the Jouanolou foliation. And in restriction to that open subset, the foliation is just a fibration by disks over a Riemann surface, which is the Klein quartic. So this is the Riemann surface, which is given by this equation, this homogeneous equation here, and so you have on this Fatou component a first integral with values in this algebraic curve, which is holomorphic. And the level sets of that integral are disks, topological disks, even though this gives you fibration which is not locally constant. So I gave you here the picture of that you can see in the book of Klein of the fundamental domain, I mean of the action of the fundamental group of the Klein quartic after uniformization. So here is a conjecture about this Jouanolou foliation in the complex projective plane. In fact, we think that the complement of the Fatou set is a very thin set. This is so in fact we think it is what we call a solenoid. It will look like locally as the product of a disk, which is called pieces of trajectories of the foliation, by a counter set. So this is what Dennis Sullivan called a solenoid. And in fact, if we are able to prove that, in fact, it's not very difficult using some of our techniques to prove that this solenoid would be of zero Lebesgue measure. So this is a very interesting conjecture that on which we are working, because it would prove that if the Jouanolou foliation, even if it is not integrable at all, so it has no algebraic algebraic leaf, it would have a first integral defined on an open set of full Lebesgue measure. So apart from or say differently, apart from a closed set of zero Lebesgue measure, the foliation would be integrable. So it would be very interesting to have that, and in fact, we can see it experimentally. So we did some computer experiments, And what we saw is that, so I'm not going to speak more about them because it's quite technical to understand, to describe them, and I will not have time. But what we saw is that, in fact, the complement of the Fatou set seem to have seem to resemble a set which is an attractor for some differential equation that was introduced by Lorentz in the 60s also, which is the following differential equation. So here, take attention that this differential equation is taken with x, y, z real numbers. So it is a differential equation in the real three-dimensional space. And in fact, it has an attractor which is depicted here. So there is this photo, and what we were able to see is that first of all the exterior of the Fatou set resembles this picture, and also we have some idea about the combinatorial structure of this set. If it is true, so of course it would prove that that this set is a solenoid. But we are working on this problem, and actually now we don't have any proof. But this is just to say that it's very plausible that we will have a proof at some moment, and it will prove that the Jouanolou foliation has this kind of almost everywhere integrability property. Okay, so I don't know. Maybe I will make some pause, because now I am going to speak about the ideas that the techniques that we use. But maybe just I want to pause a little bit if there are some questions. I think this would be a good moment to make a small pause. So I am. Okay. Right. I'm going to continue. So what I am going to speak about is about a general criterion which permits to establish that a given foliation of the complex projective plane is structurally stable, and another criterion which ensures that it has a Fatou component, a non-trivial Fatou component, which is a fibration by disks over some algebraic curve. So before saying what is a criterion, I'm going to state the setup. So we consider a degree D algebraic foliation of the complex projective plane, and what is well known is that such a foliation can be defined as in the case of the Jouanolou foliation, as a projectivization of a homogeneous vector field V on C3 of degree D. And in fact, there is a way of normalizing these vector fields. So this was something that was explained to me by Adolfo Guillot some years ago, and that served that will serve a lot here. So this is a very elementary fact, but it's really remarkable that we can always assume that these vector fields has zero divergence. So the divergence of a vector field is given by this formula. It's a holomorphic divergence. So we can always take such a vector field having this property, And if we do that, in fact, this vector field is well defined to multiplication by a constant. So we will take that vector field associated to an algebraic foliation of the complex projective plane. And our criterion now is the following. So here is the criterion. So you take that vector field and you introduce this function, which is just the log of the Hermitian norm on C3. And so you may restrict this function to the leaves of the, the integral curves of the homogeneous vector field of zero divergence. And you might look at the critical points of this, of the restriction of this function to those integral curves. So of course, these critical points can be, so generically they will be non-degenerate, and they have an indice, which in fact cannot be two. So namely, those functions, because they are subharmonic, they cannot have local maximum. So these critical points can only be local minimum. So if they are non-degenerate, I mean, they can only be local minimum or saddles. And so assume that you never have saddles. You always have local minimum on any leaf, on any integral curve of the homogeneous vector field. So then the conclusion is that you have a Fatou component. So namely, you have an open set in P2, which is a union of leaves of the induced algebraic foliation of P2. And on this Fatou component, you have a first integral to a connected compact Riemann surface of that genus. So the formula is that the genus is 1 plus d minus 1 times d plus 2 over 2. And moreover, I don't wrote it, but we can prove that the level sets of this first integral are topological disks. In fact, it's not difficult to prove that they are also bielomorphic to the unit disk. They are hyperbolic. And moreover, if the singularities of the foliation are assumed to be hyperbolic, so namely that the quotient of the eigenvalues are not real numbers, so this is what I mean by hyperbolic here. So then we can prove that the foliation is structurally stable.
You mean a restriction of this foliation on the Fatou component?
No, I mean the whole foliation. I mean the whole.
How do you know its behavior outside of the Fatou component? Your criterion does not seem to give you any information about that, or it does.
No. So it does. So the criterion is that first, if you have that this function only has local minimum as critical points along the V trajectories. Okay, so then you have both conclusions. So you have the existence of a Fatou component, and you have, if you assume also that the singularities are hyperbolic, you have that the global foliation is structurally stable. You have both. And in fact, so what is the Fatou component, in fact? So in fact, you just take the Fatou component will be, you can take the union of the critical points of this function f along the V trajectories. So this is clearly something which is projectively invariant. So you might look at this set project in the projective plane. In fact, this set is going to be a surface, a real surface, which will be transverse to the foliation on P2. right? And what we prove is that the Fatou component is just the union of the leaves passing through a point in this surface, in this transverse surface. And so the reason why we have such a Fatou component is quite simple, in fact, because if you look at the gradient vector fields of F along the V trajectory, so you have to well choose the Hermitian metric in such a way that this gradient vector field is going to descend to a real vector field on the projective plane. So then what you see is that the Fatou component is going, I mean, this surface of critical points is going to play the role of an expander. So namely any trajectories of these gradient vector fields which start close to that surface is going to how to say that? It is going to be sorry, I don't
stay away from the surface.
Exactly. Thank you very much, George. So it will stay away from the surface, and for large time it will really stay away from the surface with a distance, with a macroscopic distance. And so, using that, it is quite very easy to see that the union of the trajectories that that get out from a given critical point gives you already a disk, which is just because if you take the gradient vector fields of a function having a local minimum, this is exactly what you will see. And that the union of these trajectories, so we have to prove that the union of these trajectories describe the whole leaf passing through this critical point. And this is a quite easy argument, in fact. So the quite surprising fact is that to establish the existence of these Fatou components is not so difficult. I mean, to prove this, the first part of this criterion is not so difficult. For the second part is quite more involved. So I'm not going to speak about this because I will not have enough time. But you see that the existence of this Fatou component is already, as Sergei was saying, in a sense, I think it was your question, Sergei. So the existence of this Fatou component is already some evidence of the structural stability, because of course, this criterion, the existence of such a function, is invariant by small perturbation. So if you get one Fatou component for the original one, you will also get a Fatou component for the perturbed foliation, and so this can give you a flavor of why we have structural stability for such for foliation satisfying this criterion. Okay, so now I'm going to pass to my last slide. I am going to explain why the Jouanolou foliation in degree 2 satisfies our criterion. And so I have to say that this part is computer assisted, and we do not have still a proof, a real proof without using a computer. But I think it is interesting to note that this criterion is a priori is quite simple to verify, because in fact, to verify the criterion that I was just saying, so you have to verify that a certain algebraic function, real algebraic function, on some restricted to some leaves of the foliation, has a local minimum instead of a saddle connection. And in fact, this can be expressed by algebraic equations. to be more precise, algebraic inequations. So in the case of the Jouanolou foliation of degree 2, so this amounts to prove the following inequality here. So this is an inequality to be proved in C3, that this inequality holds on this real algebraic manifold. So you see, this real algebraic manifold, in fact, this is the set of critical points of the restriction of the function f along v trajectories. This is exactly the equation of these critical points. It's quite evident to verify this. And this equation is just saying that the critical point is non-degenerate and is a local minimum. Okay, so it is quite simple to verify that. What is not simple, in fact, we really tried a lot to get a proof that this equality implies this inequality. I mean, a proof, I don't know, using some basic inequalities, but we never succeeded. So the only proof that we have is computer assisted. It amounts to make a discretization of this surface by integer points, and to verify that an improved inequality for these approximations is satisfied, so that we can deduce that on the real surface we will get the desired inequality. So
this looks incredible, because people who are working in the real algebraic geometry accumulated a huge wealth of tools, effective tools for symbolic computation with the Grosvenor basis, which are specifically designed to answer this type of questions. Of course, you will still have a computer-assisted proof, but it will be a computer-assisted proof of a, say, incredible quality, meaning that there is some symbolic code that verifies the inequality. You never tried this?
Yes, I discussed this with people knowing these things. So, but we never really implemented that in a computer. I think it would be interesting. I think this is a very interesting project to do.
I think it's their bread. They are living on doing such kind of computations and demonstrations.
No, yes, you're right. So the thing, so one of the reasons why we do not pursue a lot in this direction is that in fact, I don't think this is a good proof. So even if it is interesting, of course, because one of the reasons is that we have also made computer experiments for the higher degree. So you see this Jouanolou foliation. So let me just go back to the slide where it is defined. You see this Jouanolou foliation. You can put a power d instead of the power 2. You get what's called the degree d Jouanolou foliation, and in fact these degree d Jouanolou foliations, we believe that they also satisfy the same kind of results, so structural stability, existence of FA2 components, etc. But the thing is that to prove that, we will need to change the function f here. So this function, the log of the Hermitian norm, is not going to work anymore for these d powers. Beginning to d is equal to
homogeneity reasons, of course.
Yes, yes, of course, you need to take something which is homogeneous here, right? And you need to take something which has some convexity property. So here you see the log of the Hermitian norm is a subharmonic function, place of harmonic function. So you will need to have this kind of properties. But so we have these functions. We have verified experimentally that these functions can be founded for d is equal to 3 to d is equal to 6, if I remember well. So we know how to find these functions experimentally. But what I want to say is that you will need to change the function f, and it will be much more complicated. So it will involve some powers, some powers with integers which are much bigger than 2. And so for the equations that you will need to solve here, you will see powers, also high powers of the coordinates. And I believe that it is quite impossible to so even for this simple case, the computer-assisted proof is quite complicated to make. So we spend, I think, over 1 year to get the final proof of that. It was quite complicated to have. So of course, maybe Sergey, if you use these other techniques coming from real algebraic geometry, maybe it would be simpler. So it would be.
In any case, it would be a demonstration without explanation.
Right. Sure. No, you're completely right. I would really love to see such a proof. Or I would really love to see an elementary proof using Hölder inequality or something like that. But you have to be really tricky, I think. I spend a lot of time on this problem, of this little question here. Anyway, so I am finished now. I really thank you very much all for your interest, and I thank the organizer of this workshop. And I hope you are all safe and healthy. Thank you.
So there is a question, Bertrand. Someone, Michael, is asking, what are the methods involved in the proof of the inequality? Was it only numeric analysis?
Okay, right. So I think so. Aurélien, who is here, just replied to that answer. So the proof of the inequality. So I was just describing very briefly. So you first approximate the surface on which you want to verify this inequality. So that surface, you discretize that surface by a very big set of integer points. So what I mean is that x, y will be we have coordinates in 1/n times the Gaussian integer, and then for each of these integer points, you verify that you have an improved inequality like this. So you will prove that you have this inequality, but you have much better. You have better than this inequality, and then by very elementary method of real analysis, you prove that in fact in the real points of this surface, in the genuine points of this surface, you will get the desired inequality. And so, as Aurélien was saying, you just reduce the proof of that inequality to verify that a big inequality like this with integers is satisfied. But for millions and millions of integer points. I hope I answered the question. This is quite elementary. This is quite basic.
But I think one curious thing is that standard numerical analysis, so that the control of error is not such a big deal, because at the end of the day, you do the computations with integers, right?
Exactly. So you really have integer points. The inequalities become integers because hopefully we have equations that are defined over the integers. So Jouanolou is defined over the integers, and the function f is defined over the integers, etc. So you have, at the end, you have really inequalities between integers. So it's really a proof. It's really a proof. As I was saying, Aurélien, I see, it is a proof, but it is, of course, it does not explain anything. So we don't understand why we have these inequalities. We just know this is true, but we don't know why.